learn how to do Sds-Page electrophoresis. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. Using the lab pad, perfect! In this lab we will focus on identifying proteins within tissues from different organs in the human body. Sds-Page is short for sodium dodecyl sulfate polyacrylamide gel electrophoresis, but in my opinion, we should stick with Sds-Page, don't you think? Sds-Page. Why do you think we call the tumor-suppressing protein p53? That's not quite right. Please try again, and remember you can check out the theory pages if you need more information. Why do you think we call the tumor-suppressing protein p53? That's right. The name of the protein is related to its molecular weight, and it was determined by the exact same process that we are going to use today, Sds-Page. As the name suggests, the type of gel we use for Sds-Page is an
Please charge your iPad.
Acrylamide gels come in different concentrations, which affects how the proteins are separated in the electrophoresis chamber. Click on the lab coat to wear it. Click on the gel modulator to go there. Do you want to see an animation explaining the details of how the protein... By running an electrical current through an acrylamide gel, the prepared proteins can be separated by molecular weight. The gel is divided into two layers, a stacking gel and a separating gel. The electrical current forces the proteins to migrate through both layers, as the negative charge of the proteins pulls them towards the positive anode. A blue dye called bromophenyl blue helps to visualize the migration. The acrylamide gel is composed of elongated polymer chains that are cross-linked to create a sieve-like structure, also called a matrix. The porosity of the matrix structure is determined by the concentration of acrylamide, which is different between the stacking gel and the separating gel. The stacking gel has a larger pore size, so the proteins move more freely. This allows the samples to easily move out of the wells and enter the separating gel at the same time. This will ensure comparable results, as all samples will start the migration at the same time. When the proteins have aligned at the top of the separating gel, the separation process can begin as the proteins start to migrate more slowly through the more dense separating gel. The dense structure of the matrix in the separating layer results in larger proteins being retained. Only proteins of the smallest molecular weight will be able to migrate to the lower part of the gel. Bromophenyl blue dyes the sample blue and acts as an indicator of the migration process. When the blue dye front is near the bottom of the gel, the current is turned off and the separation is complete. The proteins migrate through two different layers in the gel, the stacking gel and the separating gel. What is the purpose of the stacking gel? That's not quite right. The proteins migrate through two different layers in the gel, the stacking gel and the separating gel. What is the purpose of the stacking gel? That's right. If the proteins start migrating through the separating gel at different times, the goal is to at the gel, use the slider to adjust the concentration of acrylamide in the gel. Press the confirm button when you are done. That density also looks promising to me. Do you want to explore more acrylamide concentrations? Now that you have decided, let's have a look at the sample. The loading buffer contains multiple components that each have a specific function to help prepare the sample for separation. You can see these components on the screen on the wall next to you. Click on the component screen to start learning about the components of the loading buffer. Click the Start button to learn how each component affects the sample. Match the component cards on the left with their corresponding effect on the right. Great job! Now let's apply our gained knowledge to prepare the sample for the electrophoresis. Move to the sample preparation workbench. Great! Now please put on gloves to protect your hands. Pick up the pipette and add a clean tip. Add the loading buffer to the protein sample. Awesome! Now we add the sample to the thermoshaker and press the Start button to heat up the sample. First, you must place back the pipette. Great job, prepare. Let's move to the electrophoresis workbench to set up the chamber. Follow the assembly and click on the gel to pick it up. The gel has two sides, one with a lower edge than the other. The lower side has the well openings where we load the sample. It must always face towards the inside of the electrode assembly, so the samples are exposed to the current during electrophoresis. Click on the Open Electrode Assembly to add the gel to the electrode assembly. Pick up the buffer dam. Add the buffer dam to the opposite side of the gel on the Open Electrode Assembly. Close the electrode assembly. Nice. Click on the tank to open the lid. Pick up the inner chamber. Insert the inner chamber in the open tank. Pick up the running buffer. Fill the inner chamber of the tank with running buffer. Now, fill the outer chamber of the tank with running buffer. Place the running buffer back on the workbench. Click on the comb to take it out of the gel. Put the comb in the trash bin. Great job! Now that you have assembled most of the apparatus and removed the comb to expose the wells, we can add our sample to the wells. Click on the pipette to pick it up. Add a clean pipette tip to the pipette. Before we add our samples to the gel, we must add a protein ladder. A protein ladder is made from a set of proteins for which we already know the molecular weights. When these proteins separate in the gel, we can compare the unknown proteins with the known ones in the ladder to get the approximate size of the proteins in our sample. To make this easier, we add the ladder to both the first and last wells. Pick up the protein ladder with the pipette. Click on the inner chamber of the electrophoresis apparatus to get closer to the wells. Add the ladder to the first well from the left. Change the pipette tip on the pipette. Now we can add our sample to the wells. Pick up the protein sample with the pipette. Click on the inner chamber of the electrophoresis apparatus to get closer to the gel with the wells. Add the sample to the second well from the left. I will load the rest of the sample for you. I see that you are being extremely careful when loading the sample and the ladder. Click on the lid to close the tank. The last step of the assembly is adding the electrodes for the power supply. Add the blue electrode to the power supply. I will connect it to the electrophoresis apparatus for you. Add the orange electrode to the power. Click the start button on the power supply to start the electrophoresis. When the electric current is activated, the samples start to migrate from the wells and down the gel. The positive charge at the base of the chamber pulls the negatively charged samples along the gel. The samples move slowly through the stacking gel until they have aligned at the beginning of the separating gel. Raise the lab pad and click Continue between each step of the animation. The pH of the stacking gel changes the charge of glycine ions from negative to neutrally charged. The change in charge makes the glycine ions move slower in the electric field than the chloride ions, making them act as leading ions migrating in front of the proteins. This forces the proteins to travel in a narrow zone between chloride and glycine ions, ensuring the proteins enter the separating gel at the same time. The proteins have now aligned at the top of the separating gel and will now start separating across the gel. The pH of the separating gel changes the charge of the glycine ions once again. Now, glycine has a negative charge pulling the ions in front of the proteins together with the fast-migrating chloride ions. This allows the migration of the proteins to move at a faster pace and the separation process to begin. The bigger proteins are left behind while smaller proteins migrate further across the gel together with the leading ions. Bromophenyl blue acts as the dye front that moves in front of the Our proteins have now separated. But we need one more step because, if you noticed, we can't actually see the protein bands on the gel. To see them we have to stain the gel with a dye called Kumar C blue that binds to the proteins. Let's go through the staining process together, but first we need to rinse off the buffer solution from the electrophoresis chamber. I have taken the gel from the app. Press start on the shaker to start rinsing the gel. It's important to rinse off the buffer solution, so nothing gets in between the dye and the proteins. This means take the gel out of the bath. Place the gel in the gel tray on the workbench. The Kumar C blue comes next. I'm glad you've got your gloves on because this can be messy. Pour the Kumar C blue into the tray and be sure to use plenty, so we get a visible stain. Click on the bottle with Kumar C blue to pick it up. Fill the bath with Kumar C blue. Click on the gel to pick it up. Place the gel into the bath. Press start on the shaker to ensure proper staining of the gel. Take the gel out of the bath. Place the gel in the gel tray on the workbench. Okay, so that's a lot of blue dye. Let's go ahead and empty the tray for the final step in the dyeing process. Click on the container with distilled water to pick it up. Fill the bath with distilled water. Click on the gel to pick it up. Place the gel into the bath. Press start on the shaker to rinse off the dye. While blue is one of my favorite colors, we really only want to see our protein bands, so now we need to go through a bit of a destaining process. We soak our gel in distilled water for anywhere from 4 to 24 hours. It is fun to watch the color fade in the gel as the protein bands remain, but to save you time, I'll use my magic trick again to speed up time. Now that we can see our separated, click on the band that represents 53 kilodalton. Remember to use the ladder as a guide and double check. We do have a protein present around the right size in some of the samples. Remember to use the ladder as a guide and double check. We do have a protein present around the right size in some of the samples. Remember to use the ladder as a guide and double check. We do have a protein present around the right size in some of the samples. Looks like we've got a protein around the right size in some of the samples. That means that in our tissue samples, proteins of the approximate same size as P53 are present. From this, we can take the proteins from the gel and use them in a process like Western blot transfer. But for now, let's go and have a look at a few other gels like your own. Go to the gel analysis workbench to evaluate electrophoresis outcomes. Click on a gel to pick it up. Click on the variables on the screen that have influenced the results on the gel. Impressive! You have decide if the gel is usable and click on the corresponding tray. Take another look at that gel. Are you sure it doesn't belong in the other tray? Let's move it there. That's right. Smearing tells us that the concentration of proteins in the sample may be too high. It can also happen if too much sample has been added to the wells. Both of these situations would mean the bands are not comparable and the gel is unusable. Looks like you've got this under control. Now, do the same with the rest of the gels in the stack. Hopefully there are some usable gels in there. Click on a gel from the stack to pick it up. Choose the variables and click Compare to check the result. Yes, you are right. In some cases, the bands are too light because the sample wasn't properly loaded into the well. Add the gel to the appropriate tray. It may look like we could extract some results, but we want bold, clean bands. Bold bands mean we can confirm that they are comparable. When the sample is poorly loaded, it runs through the buffer rather than the gel, so the bands are not comparable. Click on a gel from the stack to pick it up. Choose the variables and click Compare to check the result. That variable is not causing the gel in your hand to look like that. Click on the lab pad for more information. That variable is not causing the gel in your hand to look like that. I suggest taking a look at the variables one more time and try to remember what we have talked about earlier. Remember, you can also have a look at the theory pages. That variable is not causing the gel in your hand to look like that. I suggest taking a look at the variables one more time and try to remember what we have talked about earlier. Remember, that variable is not causing the gel in your hand to look like that. I suggest taking a look at the variables one more time and try to remember what we have talked about earlier. Remember, you can also have a look at the theory pages. That variable is not causing the gel in your hand to look like that. I suggest taking a look at the variables one more time and try to remember what we have talked about earlier. Remember, you can also have a look at the theory pages. That variable is not causing the gel in your hand to look like that. I suggest that variable is not causing the gel in your hand. That variable is not. That variable is not. Click on the lab pad for more information. That variable is not causing the gel in your hand to look like that. That variable is not causing the gel in your hand to look like that. I suggest taking a look at the variable. Click on the lab pad for more information. Great! You are becoming quite the gel expert. I agree with you. Add the gel to the appropriate tray. Phew! I was afraid. Click on a gel from the stack to pick it up. Choose the variables and click Compare to check the result. Correct. You can see that the die front has migrated off the. Add the gel to the appropriate tray. Take another look at that gel. Right. Even if the. Click on a gel from the stack to pick it up. Choose the variables and click Compare to check the result. Amazing. In this case, the die front is placed in the middle of the gel. Add the gel to the appropriate tray. When the current is turned off too soon, the proteins may not have fully separated, so you're absolutely right. This gel looks like we are. Click on a gel from the stack to pick it up. Choose the variables and click Compare to check the result. You are right. Add the gel to the appropriate tray. Exactly. Click on a gel from the stack to pick it up. Choose the variables and click Compare to check the result. Absolutely. Add the gel to the appropriate tray. Click on a gel from the stack to pick it up. Choose the variables and click Compare to check the result. Yes, Add the gel to the appropriate tray. Click on a gel from the stack to pick it up. Choose the variables and click Compare to check the result.
Pero, kunin mo daw ang bag ko. Oo.
Click on the lab pad for more information. That variable. Click on the lab pad for more information. That variable is not causing the gel in your hand to look like that. I suggest taking a look at the variables one more time and try to remember what we have talked about earlier. Remember, you can also have a look at the theory pages. Click on the lab pad for more information. That variable is not causing the gel. That variable is. That variable is not. Awesome! Another successful gel. Go ahead and place this one in the. Add the gel to the appropriate tray. There is only one gel left. Let's have a look at it. Click on a gel from the stack to pick it up. Choose the variables and click Compare to check the result. Great job! Add the gel to the appropriate tray. Take another look. Absolutely. Let me ask you one. Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.